In this video, we're going to demonstrate a very particular trick, I would say, a trick that is used when you're trying to take the integrand of the product of an exponential function and a trigonometric function. For example, right here, we have e to the x times sine of x. Now, at first glance, it may not seem like integration by parts is going to be particularly helpful here. Because if you take the derivative of e to the x, it doesn't get any simpler than it was before. And likewise, if you take the derivative of sine of x, cosine is fundamentally no simpler than sine was. So moving the derivative and applying a derivative to one of these factors doesn't seem like it would actually help anything. But in this very special case, an amazing phenomenon will occur that we can use to find the antiderivative of this function. So the game begins just by saying, hey, I don't really know what else to do, but I do know that this is a product, and sometimes when we have products, integration by parts will work. So I'm going to go ahead and just declare that e to the x is going to be v, and sine of x is going to be u prime. It doesn't really matter because neither one of these factors is going to become simpler when its derivative is taken. Now, if you declare v to be e to the x, then v prime will also be e to the x. And if you declare u prime to be sine of x, then that also means that u, the antiderivative, must have been cosine of x. Therefore, integration by parts formula says that the result will be the product of v and u, so negative e to the x, cosine x, and then subtract the integral of u times v prime, the integral of negative e to the x, cosine x. Alright, let's just clean this up ever so slightly. We've got a negative e to the x cosine x. This negative sign and this negative sign will cancel each other out, giving you plus e to the x cosine x. Now, as we predicted, the integrand that we have achieved by using integration by parts is no better than it was before. So we just cross our fingers and say, well, what will happen if we use integration by parts a second time? Well, why not? Let's give it a try. So let's go ahead and let's call e to the x v again here in the second loop. Actually, let's make the second loop green. V, and let's call cosine of x u prime, so that in the second loop, v prime is equal to e to the x, and u is equal to sine of x. Alright, so here we are, and by applying the integration by parts formula twice so far, we have found that the integral of e to the x sine x with respect to x, from the first loop, we found that this should be negative e to the x cosine x. And so far, the second loop says v times u, e to the x, v of loop 2, u equals sine x, minus the integral of v times of v prime times u, v prime e to the x times u, sine of x. Now behold something magical that has occurred. Look at this quantity right here in the back. And notice that it is identical to the integral that we were trying to find at the beginning of this problem. And better yet, it has appeared on the right-hand side of this equation with a negative sign. Which means that we can go in and we can add this entire quantity. We can add this entire quantity to both sides of the equation. And if we add this entire quantity to both sides of the equation, the positive and negative version on the right-hand side will be completely eliminated. And on the left-hand side, two positive versions of that quantity will become two copies of the integral whose value we're looking for is equal to negative e to the x cosine x plus e to the x sine x. So all I have to do to find the antiderivative that I was looking for is go in and divide by 2. The integral that I was looking for at the beginning of this problem is equal to these two terms added together and cut in half. And we have to be careful to remember that our final answer should account for the arbitrary constant as well. So this is a trick that works especially when you have an integrand that consists of an exponential function multiplied by either sine of something or cosine of something. If you use integration by parts twice and you do it correctly, making sure that all of your signs are correct at every step, you will be able to actually rearrange the expression and solve for your antiderivative, as we have shown here.